Welcome everyone to the last lecture of this semester's quantum field theory course. We're going to today wrap it all up and put all the pieces together to describe quantum field theory for interacting fermions and bosons. At least a calculational apparatus to do practical calculations with systems of fermions and bosons. Now, the building block of any statistical physical theory are the observables. What are the quantities that you're going to predict, model, predict? Also, these are the quantities that you can actually observe in an experiment. So it's kind of key that we at least work out what we can and cannot measure. And for us, there is this list of observables known as the time-ordered Green's functions, G endpoint functions if you like. And these are defined by the full interacting vacuum and the time-ordered product of a bunch of quantum field operators at various space-time locations x1 through to xn. I'm going to draw capital Phi alpha. So I haven't drawn the alpha label. I'll put that on now. Alpha 1, x1. So the observables that we have access to in quantum field theory via scattering experiments by smashing things together are these endpoint time-ordered correlation functions here, these green functions. And these are the full interacting, and this is in the Heisenberg picture. So I'll put that in brackets here. These are the things we have access to in experiments. And now that we understand quantum fields beyond that of the single scalar boson, we actually understand fermions as well. This phi hat alpha is meant to be the list of all the fields that are relevant to your quantum field theory. So for example, a theory of scalar bosons and fermions, this phi hat alpha would be something like this. So phi 0 would be the scalar boson field operator, and then phi hat alpha x is the Dirac spinor field for alpha equals 1, 2, 3, 4. See, it's just this alpha label as a way of just putting all the field operators together in a way which compactly captures all the available fields in one formula. So they're the observables. And this is just an example here. Of course, there's many more complicated examples you could build. You could have two species of scalar boson. The kind of thing that, or three species of scalar boson, that's the kind of thing that turns up in the study of quantum electrodynamics. and say the Coulomb gauge, you have the electromagnetic field is represented by a vector of these boson fields. You might have more than one type of Dirac spinner. So in quantum chromodynamics, you have multiple flavors and colors, and associated with these different flavors and colors, you have different sets of Dirac spinners. So you can put these together in more and more complicated ways. And the task of putting them together in complicated ways that still give us meaningful physical theories that model the reality we see around us, that's the task that we'll set ourselves to next semester. For now, we're focusing on the building blocks. So, a statistical physical theory has a set of observables. That's the set of observables we care about, and it gives you a set of predictions, which are expectation values for these observables. That's already built into the way this observable is written here. So this is both the observables and the predictions. And then us theorists have got something we have to do. We have to make predictions for the experimentalists. And how do we make predictions? Because it's not going to be easy, right? We have a full interacting vacuum here. We have these fields which are evolved in the Heisenberg picture according to the full Schrödinger equation. It's not obvious how to do a calculation like this. And there's several ways around it. One is to use a computer and put things on a lattice. We won't talk about that this semester. Another is to work with systems that are perturbations of something easy where something easy is some number of copies of the scalar boson and the Dirac fermion. I don't think I wrote out the Hamiltonian for the Dirac field this semester. Could that be? Oh yeah, I did. Yeah, of course. All right, so the Klein-Gordon Hamiltonian we're familiar with. I can write it out just for old time's sake. So that's some number of copies of these. Maybe you've got more than one scalar boson, but we'll just stick with one. And also you can have some number of copies of the Dirac fermion. So plus the Hamiltonian for the Dirac fermion, which is slightly complicated because of the gamma matrices not looking so nice in the Hamiltonian picture. So you take this kind of setting where you have free systems which you understand completely. The task here is to use your full understanding of the free system to gain some understanding of the interacting system. So you make predictions by, in the perturbative framework, setting up your Hamiltonian thus. And of course, h int is the bit that allows these particles to interact with each other. And it turns out there's, thanks to the principle of locality, we're not going to allow arbitrarily crazy interactions here. We want our interactions to be local in space-time. So these interaction terms here will typically have the form of point interactions, and also point interactions of low power. And what do I mean by point interaction? I mean something where the fields only interact at a certain location in space-time. So I'll give you an example. You know, the most trivial way to get an interaction in here would be a phi to the 3. But that, I argued, well, I just declared that was unstable and you shouldn't look at it. Okay, that by itself is a pretty boring interaction because the free fermions just come along for the ride here. If the interaction was just this, then the whole physical theory would decouple into a bosonic sector which has phi 4 interactions and a fermionic sector which is just free fermions. And you may as well throw the free fermions away because they're free. But there's other interactions we could imagine. And really the simplest way to get the fermions to talk to the bosons is we want to build a scalar quantity which has the fermions talking to the bosons, right? So the one thing you might do, and is wrong, is you might try and write down something like that. It's tempting, yeah? But it's wrong. There's a category error in writing down this term. This is one operator, but this is a list of 4 operators, right? The Dirac spinor field is really 4, and there's this spinor label alpha coming along for the ride. So you have to form somehow a scalar for it to be part, to get rid of that alpha label. Now you could do something like this, you know, you take some list of 4 numbers and then sum over that alpha there. There's actually nothing particularly that speaks against that. It's not Hermitian, but we can make it Hermitian by adding on the Hermitian conjugate. But if you want it to have any hope of being Lorentz invariant, then you want this to come from a Lorentz scalar. So this turns out to be the simplest one that you can write down that's a Lorentz scalar. It comes from a Lorentz scalar. And there's more and more complicated things you could write. For example, you could take something that looks like this. Blah, 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 blah. Many, many more things. We're going to stick today with just one example. And I guess at the end of the lecture, I'll mention QED. We're going to stick with this example today. We've done that one, right? And I'm going to assume that we know what to do with that. And this is interesting. This is part of the tiering model. We're not going to do that today, but you could imagine potentially how to do this. Oh, there's got to be some gamma matrices in here. So step 1 is to focus on your observables. These are the things you think you can measure. In the fermion case, you can't usually measure just the fermion field by itself, but rather psi bar psi. Densities you can measure, but not the field itself. Because that's 4 components. How are you going to measure the 4 components of the Dirac field? You have to design an experiment that does this. And it's not Hermitian, so you know there's going to be troubles there. But you can measure the density, the fermion density, that's psi bar psi. That's this thing here. So it's pretty easy, right? We have the observables, we have the Hamiltonian, let's just solve it. But we know it's not so easy. And then we have this result that Gn can be given, we can relate to quantities from the free theories according to a very useful formula that we derived in I will find out exactly. Lecture 6 or something. Lecture 8. In lecture 8, we found a way to relate these interacting quantities to the free quantities. And I hope you remember this formula from way back in lecture 8. And where this S hat is this scattering operator. So the arguments leading to this formula here were not entirely without rigor. I mean, there was some hope that that still had some rigorous basis, and you can make sense of it in slightly less relativistic quantum field theory settings. And then you notice that, and this is a great place to depart from in doing a calculation perturbatively, because we have the Dyson series for u t minus t, right? So the next step is to simply apply the Dyson series, which gives us an infinite series for this propagator, u t minus t, in terms of the free propagator, which we know very well, and the interacting Hamiltonian term. And in some sense, that's just no more than Taylor's theorem. Let's see where I put this. Yeah. So we get this infinite series of the interacting term and the Hamiltonian evolved in the interaction picture according to the free propagator. And then at that point, we've reduced our problem to summing up an infinite series of progressively more difficult terms. So you substitute u into the place of s. And then you calculate term by term. So far that sounds all straightforward. Of course, it's around this point that things went seriously wrong. And they went seriously wrong because the very Hamiltonian that we propose right here is too strong an assumption about how the degrees of freedom of the universe interact, and we get infinities. So we actually have to think always of our Hamiltonians in the presence of a cutoff, meaning that we're not going to prescribe how every degree of freedom of the universe acts, only those up to some limit beyond which we've never been able to investigate. That's a subtlety, again, I don't want to spend too much time on in this course, with the emphasis being on all the other steps here. The discussion of the infinities, we had that discussion, but this is more properly belongs to the next course. And you calculate, so then you substitute this in, you use the cutoff version if you like. You calculate order by order, and you just calculate until you can calculate no longer. And that's your prediction for the endpoint correlation function up there. So in order to calculate order by order, if you look at the Dyson series, I guess I didn't put enough terms up here for that to be obvious. If you look at the Dyson series, you see that higher order terms have a very special form. They're time-ordered products of field operators. So this is a time-ordered product of H int. It's always in time order. T prime always happens before T prime prime. So here's T prime prime, oops, and here's T prime. So the terms that appear in this expansion are always in this time order. And in fact, even the input data is in time order. So the kinds of terms we encounter in this infinite series when we substitute it in to this formula up there are going to be time-ordered products of field operators. So that's our whole substitution, all the series, summations, expansions. The series in the end reduces to a sum of time-ordered products of field operators and integrals thereof. So our task is almost done. We just need a way to calculate time-ordered products of field operators in the interaction picture. Now for bosons, we did that by using a thing called Wick's theorem. And that's the missing piece that we need to be able to carry out this full apparatus for a full interacting theory of bosons and fermions. We need to generalize to fermions so that we can calculate full products like this. And that's our task for today. We're going to generalize Wick's theorem to the Dirac-Spinner case the result is remarkably similar, and then finally sketch out how to calculate these terms in that infinite series. So conceptually, I almost could have fitted on a board, what are the pieces of perturbative quantum field theory? The steps are, Green function, Dyson series, Wick's theorem. They're the three main ingredients of perturbative quantum field theory. I could have written just those three steps down, but of course it helps to elaborate things and give examples. And then, even though it really is conceptually that simple and dealing with the infinities, which you do on an ad hoc basis at this kind of stage of learning quantum field theory. So you might wonder why quantum field theory textbooks are so big. And the answer is, even though it is conceptually just a Taylor series formula, it's a complicated Taylor series, and we've developed ever more intricate apparatus to make that our life easier and enable us to calculate more and more terms of that Taylor series. And this highly specialized language for just this problem is what fills up the mass of your typical perturbative quantum field theory textbook. The minute we go to more interesting theories involving gauge theories, we will have to throw in an additional mass of terminology. And then if we use those to do perturbative calculations, however, we will be reduced again to very similar steps as before. It's only when you go to non-perturbative stuff that quantum field theory really explodes into a mass of material you have to learn. But conceptually, if all you want to do is perturbative calculations to match what you see in an experiment, you now have all the tools in front of you. It's just a matter of just sitting down and calculating, which is, desperately unsexy, I agree. But all right. The Dirac free field is a quadratic theory. It's completely solved. We know how to solve it. We know how to diagonalize the Hamiltonian. So that means we rather expect that there should be a way to calculate time-ordered products of Dirac field operators. And there is. It's almost the same for the bosons, but the difference between bosons and fermions is the commutation relations become anti-commutation relations. So whereas before we could just move things around that commute, every time you move two things that anti-commute past each other, we're going to pick up minus signs. It's the only difference between the boson and fermion case here. We just have to keep track of how many times we've moved things that anti-commute past each other. A little bit more complicated, but conceptually the same. And here's the minus sign coming. So the time ordering symbol for fermion operators has a minus sign. It's the only difference. Now remember, this is a matrix type object because this has an index. There's a suppressed index here. So this is actually 16 operators here. There's 16 equations here defined by that. So it's so, one gets used to just suppressing that label and just thinking it's a set of 4 operators. So beware, beware. When you put something like a time-ordered product of fields inside a vacuum expectation value, you get a Feynman propagator, which is a matrix of numbers. That's why we're so obsessed with Feynman propagators, because they turn up when we do a Dyson series. I've suppressed the label here. This is 16 numbers. Beware, that's a matrix. So remember the trick of Wick's theorem. Wick's theorem converts time-ordered products into normal-ordered products. Normal ordered products are great because if you put something that's in normal order inside a vacuum expectation value, it's instantly 0. That's why we want to do such a thing. Before I present that, I better generalize the time ordering symbol to multiple field operators, which is not entirely obvious. What you do is you put the operators in time order, and then you pick up a minus sign depending on the permutation you needed to do to put them in time order. Yeah, question?
Yeah, this psi is in spinor of 4 operators.
Yeah, the psi is a spinor of 4 operators.
Do we have to note the Feynman propagator also have these 4 alpha and beta?
Yes, yeah. Yeah. So the question is, psi is a spinor of 4 operators, so that means there's 16 numbers here. Do we have to note those numbers? You definitely do. And if, whenever you, like, well, what's going on with the numbers? Put them in like this. So there's an alpha and beta. Where are the alpha and beta in this expression? That's a scalar, that's a scalar, that's a scalar. On this, that's a matrix. So that's the connection between this spinor labels here and the spinor labels here. So this object here is a 4x4 matrix. This is how we generalize the time ordering operator to many fields. Find the permutation of these coordinates that puts them into time order. Call that permutation pi. Pi is a permutation of n things. And then compute the sign of pi. The symbol or sign or whatever you want to call it. I'm not going to define it. I defined it earlier in the course. And so that's how you do t for many size. If you have a bar, then put a bar in, right? So if you had a bar there, then there has to be a corresponding bar there. So that's time ordering. Wick's theorem is going to relate time ordering to normal ordering at the expense of introducing some propagators. That's how Wick's theorem works. But we have to define normal ordering. Again, you have to keep track of how many times you passed an operator past another, get these minus signs. So if you want to put q before p, well, because of the canonical anti-commutation relations, that has to, in order to be consistent, there has to be an extra minus sign different to this one here. And now I can present the base case for Wick's theorem. I'll also state the general case. I won't prove it. I mean, you can prove it following what you would do for the boson case. It's not a very attractive proof. Even for the boson case, this induction on the number of fields isn't really the most elegant way you can do it. Next semester, we'll see that if we use path integrals to argue Wick's theorem, then the proof is substantially more elegant for both fermions and bosons. Really quite remarkable. Unfortunately, its sort of rigorous status is slightly more questionable than the tedious proof by induction that we've done in this course. So the base case of Wick's theorem relates the time-ordered product of two field operators the normal ordered product of two field operators. And that symbol is going to be defined up above. Like that. Just by analogy with the boson case, we use this line to indicate contractions or the replacements of those operators with Feynman propagators. So I'll calculate this out explicitly, do some other cases of Wick's theorem, and then I'll quote the general result. So that's not so complicated. All right. Here's the inevitable clash of notations. If you don't use a computer to typeset your board notes, that's a plus, not a dagger. It means positive frequency. We're stuck with this notation. That's how it is. It just means positive frequency and negative frequency part of the field operator, the annihilation operator's bit and the creation operator's bit. And a little exercise later will prove to you that that's indeed equal to that. I think I'm missing a time ordering symbol here. Yeah. Yep.
Anti-commutator, because there's something.
Oh, yeah. Question is this an anti-commutator? Oh, yes, it is, definitely. Yeah. Otherwise, that doesn't make any sense. What's missing is that. Good. Yes, that was missing. And then I will put that bit together. To show you how to work with the general case. you go. So what about if we had a psi bar or a psi psi? Well, that you can calculate is equal to this is equal to 0. So with that, we actually have enough material now, I think, to extend the normal ordering definition sufficiently that we can write out the general form of Wick's theorem for fermions. So this is the kind of term that is going to occur in Wick's theorem. Remember, Wick's theorem says that time ordering is equal to normal ordering plus all contractions. So you know you're going to get terms like this if it's at all analogous in the fermion case. We somehow, this is a matrix of operators. There's an alpha here and a beta here. And we somehow have to get this, but there's the other operators in between. We somehow have to get them together before we can use this result up there. And of course you can, by paying an anti-commutation relation, you can get a minus sign to move that operator one time across and another minus sign to move it there. So you just hop it across using the canonical anti-commutation relations, paying -1 each time. Well, that's boring because -1 times -1 is 1. So let's do something slightly more interesting. Let's do a contraction between 1 and 3. So that kind of term, before you can evaluate it, you need to have this operator next to this operator. You pay 1 minus to get it past that guy. And so that's actually equal to this. And we have an expression for this Feynman propagator. So this is -1 SF x1 minus x3 normal order. And now we have enough. By this example, I mean, you have to extrapolate the definition of normal ordering from this example to quote Wick's theorem for fermions. No different now that we've got all the definitions in place. Wick's theorem is normal ordering of time ordering of operators is normal ordering of them plus all possible contractions. With the additional step that if you want to evaluate a normal ordered contraction, you have to move the contracted field operators next to each other. All right. So here's the entire quantum field theory calculation in possibly one line. So that's a schematic. This is a rough schematic of a full quantum field calculation. What does a full quantum field calculation look like? You start with your observables, which are the endpoint functions. You express them as time-ordered products of interaction picture field observables with the S matrix inside. You use Dyson to expand the top and the bottom. You then do some Taylor theorem manipulation. You've got two series. You just divide the series as a series. And then you use Wick's theorem to reduce the entire calculation to that of the integrals of normal ordered of contractions. And then you draw pictures because that's so much easier to cope with. To represent these integrals of contractions. And that's the end result. So that's quantum field perturbative quantum field theory in one blackboard. Now, the number of terms that you have to write here explodes tremendously quickly with the order. Also, sort of a less appreciated fact is that the number of locations here, that the number of diagrams you need to sum up grows tremendously as well. If you just think of summing diagrams that have the structure of a tree, then the number of diagrams you have to sum with the structure of a tree is ginormous as you add the number of leaves to a tree. So there's Catalan's number of trees with n leaves. Horrendously exponentially growing number of terms that you have to add up.
Sorry.
Yeah.
When you expand the Dyson series, for me, the fraction is 1 on the upper right side of the
Yeah, good point. So the observation is that when I schematically expanded the Dyson series here, I got the number 1, and then I got the number 1 because I forgot to put in these field operators in here. They don't go away. They're inside here. You do not expand those.
Is there a reason why you've written in the Feynman diagrams instead of lines?
The question was, why have I written diagrams with points and lines? That's because we've now got a theory of fermions and bosons, and we're going to encounter terms in this series where there's going to be contractions of fermions, which will be the solid lines in the end, and contractions of boson terms, which will be the dotted lines. I'll explain that in a second here. This is schematic. It's not meant to be accurate. It's just meant to give you the feeling for what does a full calculation look like from beginning to end. So the end result is a sum of integrals of contractions, and lots of them. Really horrendously, shockingly many terms feature in that sum. But there are patterns and cancellations in this series. So some terms don't appear. They cancel out. There's like something on the denominator cancels something on the numerator. We saw that before. And there's other cancellations that occur due to the fact that many of the terms are just the same term but with a symmetry factor. And to codify all these patterns and cancellations, we formulate the rules for what's left over in terms of things called Feynman rules. So the Feynman rules are really a collection of patterns in these terms in this infinite series here. You don't actually have to use the Feynman rules to calculate a process in quantum field theory. You could have stopped at this line here. You didn't need this picture in terms of diagrams. And certainly a computer might even find this more palatable than codifying the rules of diagrams. It may be just sort of easier to code up. It's going to be slower because there's more terms, but it may have been easier to code up. But we poor humans have to cope with this series somehow, and we do so by noticing some patterns in these cancellations. And we summarize those patterns in a set of rules, and these rules change from theory to theory. And what rules and patterns there are depends on h int. If we chose a crazy interaction with phi to the 8 and lots of fermion operators, we'd get different rules to if we just chose the simplest interaction that we could imagine. So for every h int, there's a different set of Feynman rules. You get better at working out what the rules are from the h int. And that's been the task of many physicists for the past sort of 50 years. They put in different h ints, work out the Feynman rules for the corresponding interaction term, and then try and calculate what they can and make a prediction. So this is creates a lot of work. That work's largely completed. If you write down an h int, the odds are someone's worked out the Feynman rules for it. And you just look them up. So I'm going to give you an example of an interacting boson, fermion boson theory, like the simplest one. It's not a particularly healthy theory. But as an effective theory, it makes perfect sense. So it's called Yukawa theory. The Hamiltonian is exactly the one I wrote down before. Namely, this very simple cubic interaction here between the fermion density and the boson field. So this is a theory where at the expense of two fermions, you can create a boson, or another way of saying this is that a fermion can emit a boson This is a slightly colorful way of describing the process. The boson field is sensitive to the density of the electron field. That's the exact way to describe the process. Describe the interaction. Now, if you go through and apply the apparatus of this board here and codify what kinds of terms remain uncancelled at the end of this, then you will see that you can describe every term with a diagram, a Feynman diagram, subject to some rules. And here they are. We have two propagators, one for the fermion, one for the boson. So we'll do this in momentum space. And that's one we've seen before. That's just the boson propagator. And the propagator has a mass for the phi particle, which will be different from the psi particle. When you go through the terms and codify what kind of terms can turn up, you'll notice that you always get cubic terms from the h int, right? You can only have combinations of psi bar, psi, and phi's coming from the h int terms. And so they give degree 3 vertices in these diagrams. And the value you associate to any vertex that you encounter in a diagram for the series for the green function is minus ig. We also have the possibility of external legs. External legs come from the presence of field operators in the green function up there. And there's 6 of them that we have to worry about. So if you have an external boson coming in, and it's contracted against some fermion field operators, and you associate the number 1. Similarly for the bra version. Correspondingly, you can encounter situations where you have an external fermion with some momentum and some spin. It's the S label. And in that case, an external fermion is specified by a solution to the Dirac equation. And how do you specify a solution in momentum space? Well, you need this US of P for this piece here. And it's also possible for there to be external legs where you prepare an anti-fermion. And to those you associate the V bar S of K. Similarly, for the bra version. Yep.
Which terms indicate the second Hammond diagram?
Which terms indicate this?
Operator, which relation operator? The vertices.
Here.
Yeah, the vertices in the second.
Oh yeah.
Yeah.
Which?
Written down which operator we needed for this diagram.
So this is psi, bar psi, and that's psi bar psi, and that's phi, right? Because each line, this corresponds. So the question is, which operators correspond to this diagram? So this is not a, this is an integral of contractions. So this is what appears in the Taylor series here for the endpoint correlation function. And this particular diagram here corresponds to the situation we have, well, 6 operators in this particular case, because you have a propagator here, a propagator here, a propagator here. So 3 contractions are present, but the argument of 3 of these contractions is the same, namely some particular location in space-time z. But we're working in momentum space, so it doesn't. And so just analogously, so when we did the phi-4 theory, we encountered diagrams where there were 4 lines coming together at a point. And they came in this series here from integral over z, phi z, phi z, phi z, phi z, 4 times, contracted twice. And so here we don't have the same structure in the Yukawa theory. We have 3 operators. So that actually we'll have 6 terms in such a, when such a vertex appears. We'll have psi bar psi, psi bar psi, and phi phi. And then there will be a z, z, z. 3 of the z's will be the same. So there'll be 6 operators, 3 with the same argument z. But wait, there's still more. We have to impose momentum. There's more rules. You have to impose momentum conservation at each vertex. You have to integrate over loop momentum. And then there's an additional step. You have to calculate the sign of the diagram. There may be an over or minus sign coming from the fact that some operators have to cross in order to apply Wick's theorem. So that's the rules. And we can calculate Gn according to these rules as follows. Oh, I've missed out one. Divide by symmetry factor. And that's perturbative quantum field theory for Yukawa theory. Okay. So if you apply these rules to the calculation of a scattering process where two fermions collide and then separate in the form of two fermions, then you encounter all kinds of diagrams in this sum. There are many, many diagrams with 4 external legs. Here's a couple. And I draw up these two in particular to highlight the role of this symmetry factor, this sign of the diagram. So when this diagram here is an integral over two variables, x and y, but they're actually fixed by conservation of momentum, so there's actually nothing to integrate over. And this diagram here is basically the same thing, right? These are identical particles. But because this fermion comes in to this vertex here, and it has to cross in this diagram here, inevitably when you go through and apply Wick's theorem and look at the corresponding integral, there'll be a minus sign coming from the fact that you cross these legs. And that's what's meant by the sign of that diagram there. Keep track of the minus signs. The minus signs correspond to the situation where legs are crossed. Good. I think this is probably the optimal moment with which to end the course. In this course, we've met a whole bunch of things. We've talked about relativistic quantum relativistic quantum mechanics. How do we build relativistic quantum theories? We've talked about classical fields as a proposal to get relativistic quantum mechanics by quantizing a classical field theory where it's easy to see relativistic invariance. We've studied one particular example in great detail, namely the Klein-Gordon field. We've looked at interactions in great detail for the example of phi-4 interactions. We then spoke about the case of fermions, which we didn't cover in the first half of the course, and built the Dirac field as a relativistic quantum field theory. And then we added interactions in the past couple of lectures. And I emphasized the role throughout of this process of calculating a result for an endpoint correlation function. So that's all there is to perturbative quantum field theory in this semester. Next semester, there will be an advanced quantum field theory course where we will talk about non-abelian gauge theories. That's a third type of field that we didn't encounter in this course, but one that's used in quantum electrodynamics and quantum chromodynamics. We will talk about the path integral as a way to really minimize the amount of computations that you have to do, because as you've seen, it's a horrendous number of terms you have to deal with. And we will talk about the mechanism of symmetry breaking. The objective is to give you enough information to at least understand what's meant by each term in the standard model Lagrangian. So that's the objective of the next course. But for now, let me thank you for participating in this course, and I look forward to seeing you all next semester. Thank you very much.